12.4, angle measures and segment lengths. Okay, I worry this one's going to be a little bit long. There's some tricky concepts here, but I think we'll do all right. Okay, our objective here is to find the measures of angles formed by chords, secants, and tangents. We know two of those words already. We've seen chords. We know what chords are. They intersect a circle in two places, and tangents, they're intersect a circle at exactly one point, the point of tangency. We're going to learn what secants are here shortly. And we're also going to find the lengths of segments associated with these circles. Okay. Angles formed by intersecting lines are related to the arcs. So angles formed with intersecting lines are related to the arcs formed when those lines intersect a circle. Let's look at our first theorem here. It says the measure of an angle, so measure of an angle, we're looking at degrees, formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. Okay, the measure of an angle formed, so angle number 1 here, let's look at this on our diagram. The measure of this angle that's formed when two lines intersect and they're intersecting inside the circle, here's our point of intersection, is half of the sum, so we're adding together the intercepted arcs. So this angle is the sum of this plus this, and this would be y degrees here. It didn't print very well. This angle is half of the sum of these two arcs, the measures of those two arcs, and they intersect inside the circle. This is not the they don't intersect at the center, although it would work if they did. These are not intersecting at the center. These are not central angles. Okay, so that's something to think about. This one's pretty easy. Think about it because these are, we have vertical angles here, so they're both going to be half of that. I simply add this one and then divide by 2. We're going to see more about these. Let's look at our next theorem. It says the measure of an angle, measure of our angle, formed by two lines that intersect outside of a circle is half of the difference. Difference means we are subtracting the measures of your intercepted arcs. And so here is this formula. Now, I would not think of this one in terms of x and y because we use both of those as variables, okay? And they aren't always going to be labeled in this order. So this one, if we take a look at how this works, let's look at our diagrams here. This angle that is formed, this angle right here, is formed when these two lines intersect. The point of intersection is here outside of this circle, okay, is the measure, half the measure of the difference of your intercepted arc. So when this line goes through, we have one arc here and another arc here. Those are our intercepted arcs. And the way I like to think of this is outside minus inside, or you could do big minus small. This is our outside arc. This is our inside arc. And then I subtract those and take half of it. And it's not going to matter, even if we have a line that is tangent. That line is tangent right there, intersects the circle at exactly one place. there we still have an outside arc. This is still our outside arc here, intersected outside arc, and an inside arc, right? And we can subtract those. And even when both lines are tangent, these two lines are both tangent, we still have an outside arc and an inside arc. All right. We have a definition here. Lines from a point outside a circle that go through the circle are called secants. A secant intersects your circle at 2 points. Over here, line AB is a secant. Ray AB is a secant ray, and segment AB is a secant segment. So this, notice how it goes through the circle and it intersects the circle in 2 points. That's the difference between a secant and a chord. A chord is just this in here. A chord is part of a secant. Right? So it's just this piece that intersects the circle that's inside the circle. A secant passes through the circle and intersects in 2 places. All right, the proof of our theorem up above. Why is it half the sum? Well, let's look at this angle right here. How do we know that the measure of this angle is half of this arc plus this arc? Let's take a look at this triangle right here. Angle number 1 is related to this triangle. It's an exterior angle. And what do we know about the exterior angle? The exterior angle is the sum of the 2 remote interior angles. Let's take a closer look at our remote interior angles. This is one of our interior angles, and it is related to this arc. Right? And another color. This is our other interior angle, and it's related to this arc. So if, right, it's 1/2, our arcs are, our interior angles are 1/2 the measure of our arc. Remember that from the other lesson. So if I add my 2 interior angles to get my exterior angle, right, my exterior angle equals interior angle plus interior angle, my 2 remote interior angles, and my 2 remote interior angles are 1/2 of the arc plus 1/2 of the other arc. Right, we see that here. We see our exterior angle theorem, and then we're adding our arcs, and then we simply pull out a 1/2, and it is half of those arc measures, the sum of those arc measures. So that's a pretty neat little way to do it. Drawing in our triangles. Imagine that. All right, well, it is time to pause the video and try. Actually, that's not true. We have 2 examples here before we get to try a problem. All right, let's look at the first one. We want to find the value of our variable. So we are looking at this angle measure here. I notice that I have 2 lines that intersect inside the circle. So I know this one is the sum, this one is plus. So I do the measure of my angle is 1/2 of 46 plus 90, right? And that all comes out to be, measures 68 degrees. This one over here, my point of intersection of my two lines is outside. It's outside, so that's going to be the difference. That's a minus, and it is minus outside minus inside. So this time my angle, I know the measure of my angle is 1/2 of my outside arc minus my inside arc. Okay, outside arc is 95 minus my inside arc measures z. Okay, and here what they did is they multiplied both sides by 2 to get rid of that 1/2. We'll get 40 equals 95 minus z, and I just simply solve and get z is 55 degrees, which looks pretty reasonable. We've got small, medium, and large angle measures, so that makes sense. Now it is time to pause and try the problem. Okay, these weren't too bad. We want to find the value of the variable. On the first one, our intersection point is outside of the circle. So I know it is a difference problem, and it is the outside arc minus the inside arc. My outside arc is W, my inside arc is 110. The angle that I'm looking at measures 70. Substitute all of that in, and we get the measure of the outside arc is 240. That doesn't seem quite right. 350, that should be 360. 70, 140, W minus 110, add 110, 250. Knew that didn't look right. This is why we don't skip 110. We add 110 to both sides. We get 250. And the reason that looked wrong is because I'm looking at my two arcs there, and I know they need to add up to 360. So be careful with that addition. All right, number B here is they intersect again outside of the circle, so I know I am dealing with a difference. It is 1/2 my outside arc minus my inside arc is the measure of my angle. So my angle equals y degrees. 1/2 times 110 minus 30 is 80. Half of that is 40. Our angle there measures 40 degrees. And on the last one, our intersection is inside the circle, so I know I have a sum. And so the measure of my angle is 1/2 of my two arcs here added, my two intercepted arcs added together. My angle is 35. I'm going to do x plus 30, multiply both sides by 2, then subtract 30, and this arc over here measures 40 degrees. All right, those aren't too bad. Just make sure you look for your intersection point, and then find your intercepted arcs and decide whether you need to add or subtract them. How is this used? Well, satellite is a perfect example here. Satellite's a geostationary orbit. That means that it never moves. It's always looking at the same spot, and it has a viewing angle of the Earth formed by two tangents to the equator. So we're told these lines are coming in here tangent. And the viewing angle is about 17.5 degrees. There's our arc. What is the measure of the arc that is viewed from the satellite? So we want to know how much Earth here can be seen. That's our x. We want to know what is the viewing angle, measure of the arc that is viewed by the satellite. So we know that this is a difference problem, so the measure of our angle is 1/2 outside arc minus inside arc. Now the only problem is we don't have an outside arc. But if you look at this, we have two tangents. So we know that these two arcs both equal, if we added them together, they would be 360. So this arc out here is 360 minus x. Right? Whatever x is, if I subtract 360 from it, I get that arc. So we are going to substitute that in here. There's our 360 minus x. And then don't forget that this is a difference problem. So we minus our inside arc, which is x. Minus x is minus 2x. And this time apparently we're distributing our 1/2. Right? You can multiply by 2 on both sides and get rid of it, or you can distribute it, whichever you like. I can subtract 180 from both sides and then divide by -1, or subtract 17.5 from both sides and subtract x, or add x to both sides. Either way, I end up with 162.5 degrees. That's quite a bit of the Earth that's visible. And go ahead and pause the video and try the next problem. Alright, this problem was exactly like the last problem. We have a space probe. Looking back, it can see tangent to the Earth. You can't see past the horizon there. We want to know how much of the Earth it can see. We know that its viewing angle is 20 degrees. And so we want to know how much of the arc it can see. That's x. So because it is tangent, the other side is 360 minus x. And we simply, because it's intersects outside the circle, it's a difference. So our angle is 1/2 the outside minus the inside. And we simply substitute in. I distributed my 1/2. Added x to both sides, subtracted 20 from both sides, and I got x is 160 degree viewing angle. Here, what it can see, not viewing angle, arc of the Earth that it can see. And our other problem, part B, asks us which one is closer to the Earth. Well, this probe is closer because it sees a smaller arc of Earth. The satellite saw 162.5 degrees. The closer you are, the less of that arc you can see. We saw that in the previous problems with our towers. Even when we were on an airplane 2 miles above the Earth, we could still only see, a very small number of kilometers. Also, our viewing angle here is larger because the further away you get, the less you have to look right to left to see the Earth. When you get far enough away, you can just look straight ahead and it's a little dot. When you're up close, you have to look really far right and really far left to see the horizon on both sides. So that's a little bit of a thought problem there. All right, not too bad. 2 pages down. Let's see what the third one holds in store for us. All right, we are going to be talking about intersecting chords, intersecting secants, and secants that intersect a tangent. And we are going to use these to find lengths. So the first half of our lesson was angle measures, and the second half of our lesson here is lengths. The lengths of our segments of our chords. All right. We have a point P here. And we can draw 2 segments to a circle along infinitely many lines, right? I can go from P and I can go to A1 or A2 or A3. And then I can go from P and go to B1 or B2 or B3. This takes us to our theorem here that says for a given point and circle, the product, so that says multiply, of the lengths of your segments, now this is important, from the point to the circle is constant. So if we multiply the length of those segments, we're going to get the same number. What this says is that we have a point here. And if I take A times B, so this length, and multiply it by this length, that it is going to equal C times D. And that is going to be true for any chord that goes through that point. Multiplying the two segments from the point to the circle, right? We go from our point P to the circle, that gives us A. From our point P to the circle, that gives us B. The same with C and D. Now, this is an important idea because this one's the easy one. Let's look at the next one. Same problem, only a little bit harder to see. You're going to have to think about these a little bit more. This time our lines intersect outside the circle. Inside the circle is easy. Outside the circle, the same holds true. The product of the two segments from the point to where it touches the circle. So let's look at this first one. Where does my top line here touch the circle? It touches here. Okay. That is W plus X. That's where the first one goes through. That's our secant. And then where's the second line? Where's our second point? Well, it goes from P to the other side of the circle, and that happens here at W. So this is the left point times the right point. Now, if you look back at our first circle here, we have our intersection point, and we have a left point and a right point, and a left point and a right point. This is the same thing here. For our bottom line here, we have a left and right point on the circle. If we go from the point, there's our left point, y plus z, to our right times our right point is just y. So don't think of these again as w plus x and w, because again, they're going to be labeled with whatever variable the problem feels like labeling them, or whatever number. Think about what the theorem says. The theorem says that from our intersection point to the 2 points where it intersects the circle. Okay, let's look at our third example here. Our intersection point is outside of the circle. And let's do the bottom line first, because we recognize this. There's the 2 points that it intersects the circle. All right, so there's our left point, right, times our right point. Okay, y plus z is how we get to our left point. Y is how we get to our right point. Let's look at the top up here. This only intersects the circle in one place because it is tangent. All right, we need it to intersect the circle in 2 places. Now, you can kind of think of a tangent as 2 points. The line comes in, touches the circle, and it touches the circle as it's going out. So our length here is this length times this length. and that's where we get t squared. So our left and right point are the same thing. Right? So you just remember that tangent, this is what happens when it's tangent. We just square that length because it gets counted twice. We need 2 points on our circle and we only have one, so it gets counted twice. So if we think about this, if we have chords, your segments are equal, the products are equal. If we have secants, the product of the secant and their outer segments are equal. And the product of a secant and its outer segment equals the square of the tangent. Those are these in words. I often find pictures much easier. From the point to where it touches the circle, and it touches the circle in 2 places. So you have to go to your left point and your right point. The proof of this is actually kind of neat. You know, I enjoy proofs. All right, let's look at this here. We have our 2 lines that intersect each other. Right here, these intersect each other. And we're going to draw in some auxiliary lines to make triangles, because that's how we do everything, right? And if we look at angle A, right here, it intercepts this arc. And I know that angle A and that arc have a relationship. Their measurements, the angle is half of the arc, because it is intercepted, its vertex is on the circle. Well, let's look at angle D over here. It intercepts the same arc. And we know that inscribed angles that intercept the same arc are congruent. Well, we also have intersecting lines. And you should be going, vertical angles. Vertical angles are congruent. And then we have a little something called the third angle theorem that makes all of those angles congruent. So we can say that our triangles are similar. We don't have any lengths, but we can say they are similar. And we know that corresponding sides of similar triangles are proportional. So we can write this proportion here. And when we cross multiply, look at what we get. We get the formula from our first theorem up there. All right, let's look at an example. That's kind of fun. I like that. Let's look at our first example here. Find the value of the variable in circle N. Okay, well, they intersect outside, and I know I'm looking for lengths, so I know I'm using these formulas. I want to know where they intersect the circle on the left side and then on the right side. Okay, so one of my lines measures 6, the other one measures 6 plus 8, so I multiply those. And then on the other side, going to that point measures 7. Going to my other point measures 7 plus y. I just do the math, distribute, opposite operations, and y measures 5. Now we check, is that a pretty reasonable length? Yeah, it fits right in that, the lengths with the others. All right, let's look at our other example over here. Intersects outside of the circle. So I know I'm trying to find the 2 points that it goes to. Okay, the bottom one here, that's 1 point. My other point's there. So my short line is 8. My long line is 8 plus 16. And then I see a tangent here. This one's tangent. So I know I square that. So that one's z squared. And then anytime we have a square, we're going to square root. And z is about 13.9 units long, which fits right in with everybody else. All right, pause and do the last two problems. Okay, these aren't too bad as long as you are careful and label everything and write your formulas. First one, our intersection point is out here, and we know we need to find out where, from the point to where it intersects the circle, we have a left point and a right point for both top and bottom line here. And it's just the distance to the left point times the distance to the right point equals the distance to the left point times the distance to the right point. Our top line, to get to the left, 20 plus 14. To get to the right, it's just 14. The bottom one, to get to the left point, it's x plus 16. To get to the right point, just 16. Do my math, opposite operations. X is about 13.75, and that fits right in with all of the other lines. Okay, this one is exactly the same, except our intersection point is in the middle, and these are the easiest ones to remember, because to get to, we still have left points and right points, and I called this one left and right. Doesn't matter. If I turn my paper, it's left. Okay, so to get to my left point, 6.5. To get to my right point, m. To get to my left point, 3. Right point, 7. Simply substitute in, do the math, and m is about 3.2. These are not difficult concepts, especially finding the segment lengths. Okay, just remember your left times right equals left times right, the distance from your intersection point. Identify your intersection point. The most difficult part is going to be the angles, and just find your intersection point. Is it inside? Is it outside? And then identify your intercepted arcs. Color is your friend here. And label everything. So you're going to identify your intercepted arcs and then figure out which formula you are using. Always label, write your formula, substitute in. If you are careful with these, you will do just fine.